Swayam Prabha. Digital India. Educated India.
So, good morning. We will today start discussion on magnetizing current of the transformer. So, I am going to discuss two topics now. One is the nature of the magnetizing current, because iron is a non-linear element. So, the magnetizing current, though we would in our equivalent circuit we have approximated it by a sinusoid, it is actually not a sinusoid. So, it has actually fundamental and some odd harmonics present. So, that means there is a distortion from the sinusoidal waveform, and the cause of the distortion we have to understand, and we have to do some, we will try to develop some understanding on that. The other aspect that I want to discuss is inrush current. That is also a very specific phenomena associated with the transformer. When you energize the transformer, as the word inrush signifies, there would be a rush of current, heavy rush of current, and then that current would gradually come down to your no load current. So, that is another non-linearity which exhibits itself due to iron, iron being the primary dominant element of the transformer. So, these two aspects we need to understand in this lecture. So, let us begin with the more the simpler one, the magnetizing current of the transformer. So, I have a picture here, if you see this picture here, this is the BH curve of the transformer. So, to recall, this is my B, this is my H, and this is my B. Now, B I rescale y axis by multiplying it by A. So, it becomes flux, and for H I rescale it by I rescale it by a factor of L by N, because H into L is equal to N times of I, the Ampere's law. So, I rescale it by a factor of L by N, where L is the, in a single phase transformer, L is the average path of the magnetic flux in the core, and I get current. So, this is phi I diagram, and this is the hysteresis loop associated with it. Now, the magnetizing flux is shown by this waveform here. If you see this waveform, this is the magnetizing flux waveform. So, this peak has to match with this peak, this peak has to match with this peak. So, that means what I am trying to sort of say, is that this is not one BH curve, it depends upon what is your peak flux that is going with your transformer. So, for, if I first draw curve like this, this is a BH without considering hysteresis. It's only iron is a nonlinear element and it tends to saturate, the B tends to saturate towards B max. And earlier I had said that if you recall, I had said that there is a knee point associated with it. So, the knee point is if you take a tangent here and when it saturates, you take a tangent here, where it intersects, that point is sometimes called as B knee and this would be H knee. This is to define, I mean knee is where it turns, just like in our leg where you can bend it, you know. So, where the characteristic bends, if you want I will draw it slightly more better way than this. Should not reduce, should always increase. But the later on, once it has gone deep into saturation, then any change once it has gone deep into saturation, then any change here and here. So, say this is B 2, this is B 1, this is H 2, this is H 1, then B 2 minus B 1 divided by H 2 minus H 1 has a slope of 10 to the power 4 pi into 10 to the power minus h. So, therefore, it almost looks like flat line, it almost looks like a flat line. Here, however, in this part, unsaturated part, so let us call this one say B 1 dash and so let us call this B 1 dash, let us call this H 2 B 2 dash, H 1 dash, H 2 dash. So, here if you look at it, this is saturated. For unsaturated, B 2 dash minus B 1 dash divided by H 2 dash minus H 1 dash is going to be equal to mu 0 into mu r, and as I said mu r may be like 1000, 10,000. So, this slope here, this slope here is very large, this slope here is very small, and where these two. So, if I wanted to like approximate, if I wanted to say approximate the BH curve by two straight lines, then what would I do? I would have to fix, I would have to, so this is my BH curve. So, I would have to fix some point until which the description is B equal to mu 0 mu r h, and I would have to fix another point. So, this is until say h up to which I will call it as h knee, and here I will call this as minus of h knee. H knee and minus of h knee. And other thing is, I would need another line another line where the B, or if you want I will write it as, because otherwise I will have to write an offset. I mean I will do that both. Okay. Let us say this is deliberately I am keeping this as h just to show what the advantage of writing delta is. So, the equation of this, the slope of this line is just mu 0. So, B will be mu 0 h, but offset is when h is equal to 0, the offset is the some B naught. I'll write some B naught for this, but this description is valid only in the region where h is greater than h knee. H is greater than h knee, and then if you want to write for h less than minus of h knee, that means you take this line and look at the corresponding this one here, then the B will be minus of mu 0 mod of h plus of P naught. Why mod of h I have taken? Because I just want to say this line is minus of this line, but the h here is actually in this direction. This is B, this is h. In this direction h is negative, but I am just trying to take this line and write as minus of that. So, then the h being negative, I have to use minus of, I mean the mod of h, and then this B will come out to be proper negative. So, I can, if I write this, take the minus inside, then minus of mod of h is in this direction is h itself, and this will become minus the. So, h is equal to minus of h of knee. See the why I am writing these equations this very neatly is that I want you to learn how to translate a graph into equation, a equation how to translate into a graph. These are some basic skills that you should try to fix, you know. Many times I have noticed that in our school education, graphing is not a concept we understand very easily. The reason is because we are writing entrance exams and then subjective exams in the board and things like that. So, somehow more skill is on problem solving is where the our effort is, but to develop models is a new thing that you are picking now when you have got into the engineering stream, and to develop models you should be able to, like for example, the characteristics of the iron BH curve, you should be able to write equations, because once you write equations then only you can simulate it in a computer, you can write something about it. And so this becomes a kind of a art or a practice, and there is not like, there is no one way of writing this equation. I could have derived it in some other way also, but the process one has to pick up, you know, how to write this equation. That process one has to, one has to pick up. So that is why I spent, it is not like I am really going to use these equations, but I want you still to pick up this art of, there are many things other than just plain simple magnetic circuits and transformers and induction machines and single phase and three phase systems and active power and reactive power that you have to pick. You have to pick from a course, that is the core learning that you get, but there are other side skills, just like when you have food, it's not you don't just eat chapati and bhaji, you may have a bit of salt, you may have a bit of chutney, you will have a bit of this, bit of that, and each of them plays a very important role in making your plate, in making your food. So something like that in this course also, something dominant you are picking, no doubt about it, but try to pick some other things also, in terms of modeling and analysis. Try to see some interesting things that keep going around. That is my like plain request or suggestion to all of you. Okay. So coming back, this is my so this becomes my set of equations. There are lot many, but if I just say for the this is this is the linear region where it has not saturated, unsaturated, and this is the region where it has undergone this is the region where it has undergone saturation. Now, in the unsaturated, when I take delta on this equation, I will just get delta, this is equal to mu 0 mu r h, h is between h ni and minus of h ni, and if I look at the delta of this, I get delta B equal to mu 0 h, and if I look delta of this, delta B will again this constant B naught, this constant, when I take delta, the constant B naught will go away. So, when I take delta of this equation, the other equation, even here I get B equal to delta H. So, the point is so the point is H, I can write this as H greater than H ni, or I can write H, yeah, this is good enough. If I say mod of H is greater than H ni, then when H is positive, mod of H mod of H is positive. So, H will be greater than H will be greater than H ni, and when H is negative, then this is minus of H, mod of H is minus of H, negative numbers minus we have to take, minus of H is greater than H ni, which translates to saying that H is less than H of ni. So, if this is the ni, then you describe it here. So, this is the simplistic model. Now, the point is, if this is the simplistic model and you do not want to have any discontinuity, you do not want to have any discontinuity in your set of equations, you want nice continuous equations. There is of course a corner point. I am not saying that it is differentiable here. It is differentiable here, straight line can be differentiated here, the differentiation is the slope. Here there is no differentiation possible, but it is continuity is there. So actually I should sort of shade this thing, this part is not there I actually speaking, and actually speaking this part is not there. Similarly, strictly speaking this part is not there and this part is not there. Now, if I want a simple model which is free of discontinuity, then where is my knee point? My knee point is here, the H, this has to be the H knee, this has to be the H knee point. So, this is why ANSI has defined knee points as the taking the two slopes at 0 and this, and then looking where they touch, that point is called knee point. But then you should connect it with the actual BH graph, right. I mean, you should connect it with the actual BH graph. So, therefore, what you do, H knee is just this value, B knee will be now defined as the actual value of the B for that material at H taken as H knee. And though this may look a too big a difference here, it may not be this big, that may be my drawing skill. So, I think now you see the reasoning. I could have just said where these two lines intersect, that is called the knee point, and this is H knee and B knee. But I think now you see why the standards have defined it that way. That is another thing I sort of want you to think about, why things have been, even when things get standardized, why have they happened like that, what could be the reason behind it. Because maybe tomorrow you may be writing standards, world is continuously changing, renewables are coming in a big way, we do not know what is the electrical industry of the future tomorrow, and you may be doing, you may be going to do lot of things, new things you would be doing, and you would also have to write standards and things like that. So, you should be able to take the learning here and use it, one thing wherever you need to directly use it, and also translate it into something new in future which you may have to do. So, there is today some lecture, there is some philosophy also we are discussing, but it is important. Okay. So, let us come back now to this curve. This okay, I was actually what I was trying to say, that so hysteresis, I was discussing hysteresis. Now, suppose this is phi and I, and suppose the transformers phi max is only this for some reason, this minus phi. Then the curve that you are going to actually see is this, due to hysteresis effect that we have already discussed earlier, that there are domains or grains in the iron, and they need to be aligned, and that is that requires work to be done, and that work which gets done has to be dissipated as heat, and that leads to some remanence, and to get the flux back to 0, you actually have to apply a demagnetizing current to get it back to 0, and so on. When you talk of magnets, their remanence is like extremely high, they may require much more good magnets which cannot be quickly demagnetized also. So, they may require a lot of H application to demagnetize them, otherwise they may lose magnetism very quickly. So, magnet design is a different topic, but the same concepts also play a role here. In the same concepts also are required when you talk of the design of magnets. Here, what we have done now is basically we have said that this is the work done here, this is the work done when if you talk in terms of B and H, then the integral of this area under this is actually per, I think we did this per unit volume, this is the work done, or per unit kg, this is the work done. I think it is per unit volume we had derived that, and this creates a loss component. So, because of this, normally when we write the equation of a plane inductor, we will write it as j d omega I by dt, and if we want to write a phasor equivalent, we will use the Heaviside operator, write p equal to j omega, and write the phasor equation as j omega L I phasor, which is to say that V leads I by 90 degrees, but or I lags V by 90 degrees. But due to hysteresis, and I will show it graphically, due to hysteresis, because there is a loss associated with. So, 90 degree lag means power factor is 0, power factor is 0 means there cannot be any active power dissipation happening in it. And if you remember in equivalent circuit also we had shown this, of course, there is eddy current also to be accounted for, which I am not right now worried about, but we had shown this as JXM and this as RM. So, this there has to be a component which is, if this is V, there has to be a component which lags this thing, and there has to be a component which creates a loss part of it, and the together summation of phasor summation of that, the together the phasor summation of this becomes the no load current, and its power factor is less than, due to hysteresis, the power factor, due to hysteresis the power factor should not be 0, and so I should lag by less than 90 degrees, maybe 78 degrees or something like that. Now, if I increase the phi m, this is the kind of hysteresis loop that I will get. So, remnants flux and other things will also tend to increase and things like that. And if I do this, sorry, this figure is not come out, this is better. So, if the phi m is increased further, then the hysteresis area that it is covering is even more higher. So, the RM will tend to be more and more you push into saturation, bigger problem you are going to have with respect to the non-linearity of circuit. So, now let us come back. We have designed a transformer for some phi m under normal operating conditions. So, I could have shown a family of hysteresis curves, but I have shown only one hysteresis curve here, and you can imagine there is a underlying actually base nonlinear curve around which knee point and everything else is described, then that has been converted into through experimental measurement into hysteresis cycle. But suppose I wanted to only have a linear approximation, this is approximation, only a linear approximation, then this dotted line, blue dotted line would indicate the linear approximation of this circuit. Now, because in an ideal condition V equal to d lambda by dt, so therefore, the magnetizing flux which is n lambda being n times of phi. So, let us say that if we apply V sinusoidal, we are going to get a sinusoidal magnetizing flux, which is shown here. I have taken it. So, we are starting with for analysis we are saying let the flux produced in the core of our transformer be a sinusoid as shown here, this being phi m, this being minus phi m, this phi m, this being minus phi m. Now, let us say that see I am going to when I apply a sinusoidal flux undergoes a sinusoid, it will keep tracing this same hysteresis curve again and again and again and again and again, because the flux is going through this. What I want to find out is, if this is what is happening to flux in time, what is happening to I in time. This is what I have shown here also, already drawn, but I want to see what is happening to I in time. So, I should begin at some point, right? I mean I should begin at some point. So, let me say that I begin at this point, let me use this point. I begin at this point, let me call this point as A point. So, this becomes my A point. So, what happens here, the flux is 0, but there is some current OA. So, this is that current OA which is there, that means flux is 0, some current is there as per this definition. What is this current? This current is required to bring this remnant flux to 0 value. So, demagnetize it, otherwise from the negative cycle of it, the magnetic dipoles will be somewhat aligned in a negative direction. You have to make them random to give a net 0 flux. So, you have to apply a positive current which is shown here. Then I start tracing it here. So, I start increasing the flux. When the flux is increasing, this flux is increasing, it reaches here. On this curve, it is going to trace this path. This is phi versus I, this is phi versus t, difference is there. This is phi versus t, phi versus t is growing like a sinusoid, but phi versus I, does it have a choice? No, it is defined by the hysteresis curve. It is going to the I, that is phi, you had a choice and you took a sinusoidal with respect to t. Now, I also you cannot take sinusoidal with respect to t. I versus t is going to be decided by the fact that you are going to trace, this is your road, this is your highway. On this highway your car is going, so to say. If it is turning, your current has to turn in some sense. So, starting from a positive value, it will trace and reach here. So, starting from a positive value, it will trace and reach whatever is this I max here, this is that I max. So, let us call this point as B point, then this is my this is going to be my B point. Now, here onwards, so I am going like this, I reach this point. Now, the flux starts reducing, phi versus t here sinusoid, the flux starts reducing. So, if the flux starts reducing, what happens? Current is also going to reduce, which is fine, and when I come here, the flux is positive, but the y axis, on the y axis current is 0. So, therefore, at some point here, I am sorry, at some point here, which this is my point number A, B, C, this point C here, at this point C here, the flux is, this is C point here, flux is positive, but the current has become 0. So, the flux has not become 0, current has become 0. So, what will happen? Now, the current will turn negative, the flux continues to reduce, right, because the flux is what is applied here in some sense. So, the flux is going to continue and reduce to 0, this is where flux will become 0. So, this will I will reach the D point here, let us call this point as D point. So, when the flux reduces to 0, what happens to current? Current has a negative value, and since this offset and this offset are going to be the same, because it's you could have gone this way also, it is not like you have to always go this way, that is not going to impact your analysis, it is not a directional element in any preferred sense in that sense. So, this OA should be equal to this OD, and I am sorry, flux is 0 and this is the D point. Now, from this point D point, I will go all the way like this to E. From D point I will go all the way tracing this curve, it will be come here D to E, it will go. E will at E point the flux reaches its, this is my E point, the flux will reach its max, negative max, the current will reach its negative max, the current will reach its negative max, and then I will trace back here in this, I will trace back here in this way. When the flux is at point F, the current is 0 because I am on the y axis. So, this point here current 0, flux negative is my F point, and from F point I will have to, I will be tracing this way and come back to A point. So, I come back again to A point. So, if you look at this picture, you would see also that because initially the slope is high, the current is not rising rapidly, but when you come closer to saturation, slightly like a nose, like a nose, the current tends to increase a bit more rapidly, and then it follows, it decreases also, current increases more rapidly. Why? Because the slope of the BH curve reduces. So, because the slope of the BH curve reduces, current also drops down a slightly bit rapidly here, and then the negative half cycle is, it is a odd kind of symmetry, right. I mean the negative half cycle is a replica of positive half cycle, and you get something something like this. So, this curve is not sinusoidal, this current curve is not sinusoidal, and how, in what way would have, how would you have got a sinusoidal current? You would have got a sinusoidal current if the BH and now if your B versus time was sinusoidal, that means flux versus time if flux or B versus time was sinusoidal, then the H would also have become sinusoidal, because it is just a scaled replica. So, therefore, this phi would have become, and I also would have become a sinusoidal current. For this, it has to, for phi and I, in that case if this is designed by a sinusoid, magnetizing current is also going to be sinusoid in phase with the phi, 0 crossings exactly match, rising, decreasing, and again the rising kind of thing. So, what I am trying to sort of say here is, if this was the BH description approximation, then the I curve would have looked like this, because I have connected these two dots passing through 0 by symmetry. I max whatever is here, same I max I would have got, but it would have become a sinusoidal like this. This leads a bit further because there is a positive current. So, you can see the shift, I have shift as if this has slightly been shifted, there is another thing that is happening here. So, there is something like that which is happening here. So, now coming to this analysis of this waveform, this waveform is number one non-linear when it is periodic. So, we know that from our Fourier series background, which we usually do in the first year mathematics course. You would probably have done it, or you may have to do it, and some places it is also covered in the network analysis. you know that if there is a periodic waveform, and how is a periodic waveform described? F of t equal to f of t plus capital T. Capital T is called the time period. So, any periodic waveform, it has to satisfy some conditions known as Dirichlet's conditions. In these waveforms that I am discussing anyway satisfy them. So, no need to worry about it. Such waveforms periodic waveforms, even if they are not sinusoidal, can be written as so if f of t is equal to f of t plus t, actually you can write it as f of t plus n t, n is an integer, then this f of t can be written as summation of a I'll explain to it 1 minute. So, I 1 I n equal to 1 to infinity n equal to, this Fourier did it long time back, you know, this is not something very interesting thing, but beautiful, actually has foundation of electrical engineering in some sense, Fourier analysis, especially when you deal with nonlinear circuits. So, the A0, it says that you can write it as a DC value, which is the A0, which is the average value and then you multiply and then the second term is, if I expand this further, I will get this first as A1 cos of omega naught of t. Similarly, from here I will get B1 sin of omega naught of t, and then additional terms will be like A2 cos of 2 omega naught t plus A3 cos of 3 omega naught 3 and so on, and plus B2 sin of 2 omega naught t plus B3 sin of 3 omega naught t and so on and so forth. So, this term here, the first term here, this is called as DC, this one is called as fundamental component. So, fundamental component omega naught is 2 pi by t, the time period of the waveform. So, that is why the word fundamental, this is happening at frequency omega naught, which is 2 pi by t, which is the basic property of this waveform. So, therefore, it is called as fundamental. This is called DC because this is constant, and you know this, that this can be also represented as some A cos of A1 cos of or C1, if I want to use another, instead of A and B I will write C1 sin or cos of omega naught t plus phi 1. So, group them, na, some you well conversant with that, and then these terms are called as harmonics, the multiplier ones, the n omega naught thing, n integer and greater than 1, these generates harmonics. Now, so far in our study there was only one frequency which is fundamental, everything phasors were also at the fundamental, all signs were also at the fundamental. First time today we are seeing that because our waveform is periodic, but not a sinusoid, we will have to take recourse to Fourier series and write it as a fundamental component. Just for example, in this case I have written it is 50 sin of omega t minus 17, and then the waveform is going to look like all sines because of the odd symmetry. The odd symmetry means f of t equal to minus of f of t. If a waveform is like that, it is Fourier series. If you go a bit more details into the Fourier series, you will see that it has only sine components, and if it has what is known as a even symmetry, the even symmetry means f of t is equal to f of minus of t, a waveform like this. This waveform is having a even symmetry, and a waveform like this is having a odd symmetry. So, this is odd symmetry, this is even symmetry. So, a waveform which has even symmetry has only cosine components. You think about it or go and consult some book which teaches Fourier series. That is another thing that I want you to pick up, is to take different books and read from there, not just from video lectures or just one book, go in, dive deep. That is what I am trying to sort of say, dive deep. Now, so this will have another interesting thing about this is, I am not going to derive it, but another interesting thing is, if you go a bit more details of it, in general you can have both all the harmonic frequencies, second, third, fourth, fifth, so on. But magnetizing current, when we analyze this waveform, we find that it has only odd harmonics present in it. So, you have with an amplitude of 50, that is RMS value 50 by root 2, a fundamental component with an angle of 17 degrees lead, because this is fundamental, but this is a 0 value here. So, therefore, a lead of 17 degrees. Then I have something which is third harmonic, which is coming with an angle of 8 degrees. Now, you see frequencies, we are all phasors are all only defined at our fundamental frequency level, and you can also define phasors at harmonic levels and so on and so forth, but in one analysis you cannot club phasors of different frequencies. So, these all harmonics actually we fortunately they are only creating losses for us, and we are showing it approximately by a Rm. Whenever we draw phasor, we mean only the phasor corresponding to the value of 50 by root 3. And then another thing that you will see in this just a sample description of this harmonic analysis done for this phasor is that this is like say 28% of 50, this is like 28% of 50. This is like 18% of the fundamental, this is 28% of the fundamental. So, the harmonic levels decrease, amplitude of the harmonic levels decrease. Qualitatively, I will explain you like this, that my dominant nature is, even though I have a nonlinearity, the nonlinearity is only a small deviation or some deviation from sinusoid. So, the dominant thing will always be at the fundamental, but when I draw that something at fundamental, it will not properly depict this. So, then I have to add harmonic terms to them, those correction terms will keep decreasing usually. So, that is why these amplitudes will sort of keep decreasing, and this is one approximate, of course, this whole thing goes up to infinity, but this is one approximate description of the magnetizing current. So, you see that not only it has odd harmonics are present, phase displacement of 17 degrees from the fundamental implies that it lags the voltage by 90 minus 17 degrees, which is 73 degrees. So, I just said earlier, if you remember in the early part of the lecture, if there was no hysteresis, you would get there cannot be any losses. Eddy part I am keeping it aside, I am only right now looking at the hysteresis part. Then if there is no hysteresis loop trace, there will not be any hysteresis, this thing, in which case you are it would be BH curve would be a line something like this, and then you would get current lagging by 90 degrees. But now, because there is a loss associated with this area per cycle, so therefore, it cannot lag by 90 degree, the lag has to be less. So, that is created from this part, the I of t is something sin omega t plus 90 degrees, because V is equal to j omega L I. So, the ideally it is with respect to 90 degrees, but because of the lossiness 17 degrees fundamental has got offset, and so a displacement of the 17 degrees for the fundamental implies that it lags voltage by 90 minus 17, in this case 73 degrees. So, the 50 cos 73 degrees or 50 by root 2 if you want to talk in RMS value corresponds to this component will be responsible for this component will be responsible for the hysteresis loss. Eddy loss is going to be in addition to it. So, it may appear to you that my goodness, this is quite a far deviation from sinusoid, and 28%, 18%, these are like significant amount of harmonic contents. Yes, true, that is very true, but this is for no load current. And how much is usually the no load current? No load current is approximately 5% of the full load value. So, the load current will be the harmonic load current waveform is sinusoid, it is not dependent upon my this iron element, it depends upon the load. If you have a voltage which is sinusoid, and if there is a motor connected or a resistor connected or a proper inductor, normal inductor connected, then the load current will always be significantly sinusoid. So, the no load current adds on to it. So, there finally what happens is the load current with respect to the load current, because the no load current is only 5% and then 5% something is the harmonic. So, actually in the actual waveform, if you meter it, if you see it on a CRO, you will see that it is far less. The current is magnetizing current has the harmonic content in the full load current is far less, though in the no load current harmonic content is high, the harmonic content in the full load current is far less. And at over voltages, core may be driven into saturation. So, that is why over voltages are not good for our transformers. When you design a transformer, you do not want to unnecessarily put too much of iron. So, you will choose your phi m to be close to knee point. Now, if you over voltage, phi m is close to knee point and you apply over voltage, what will happen? The flux will increase. So, the phi m will increase. So, the transformer will be pushed into saturation, and when the transformer is driven into saturation, the curve is delta B is equal to mu naught delta H. So, suddenly for that higher flux, the currents will tend to increase significantly, and so may be driven, harmonic content may increase significantly, and harmonic content will only create losses. It is not something that we desire. So, therefore, we should not allow overfluxing or over voltages on transformers. That is why the grid voltages, everything as voltages have to be for so many reasons, insulation, overfluxing, so many reasons, we want to keep voltages within say plus minus 5% or something like that. We cannot allow too much deviation in the voltage, otherwise equipments, power apparatus will not function appropriately. So, we will stop here for today and we will take up in the remaining part next time. Thank you.